Okay, welcome to our next video. Here we're in section 2.6, which we're talking about marginals and differentials. We're finally moving away from minimums, maximums, optimization, and we're going to look at a different way that derivatives can be really helpful. Let's start with this idea of marginals. And so what is a marginal value? Well, marginal is a term that's used in economics to just describe the change in a value associated with a specific change in some independent variable. What does this sound like? What does a marginal value sound like? Well, it's a rate of change. Hopefully you got that from this definition. It's really just a rate of change. It's how does one thing change as another thing changes, which is exactly what a derivative is. So if you ever see that word marginal in one of your homework problems, it's really just asking for the derivative. So you might see something like marginal cost. Find the marginal cost. That's really just asking you to find the derivative. It's just some things to keep in mind as you work through marginals. If you ever profit, how do we calculate profit again? Profit is just revenue minus cost. And then remember with revenue, how do we calculate revenue? Revenue is price times quantity. You might need those. You might need to remember those as you go through some of these equations, because if it's asking for marginal revenue, you just need to find the derivative of your revenue equation. So let's move on to differentials. What are differentials? Well, to understand differentials, we need to go back and revisit Leibniz notation. So if we have y as a function of x, what does this notation mean again? dy over dx, it just means it represents the derivative. And remember, the reason why is because this notation represents your change in y as your x changes. It comes from that slope formula, which is exactly what a derivative is. It's a rate of change. So to get a differential, all I'm going to do is multiply both sides by dx, which leaves us with dy is equal to f prime of x times dx. And this really is all a differential is. It's just a different way to write your derivative formula. Differentials represent this idea of multiplying the derivative by dx, or the change in x, in order to get your dy, or your infinitesimally small change in y. So why would this be helpful? Let's say you have a function and you want to know how the y value will change if you tweak your x value. If you change your x value slightly, what effect will that have on your output value? What that effectively is delta y. Delta y represents your change in y value. And we can actually calculate this straight out, right? I can just take my new y value and subtract my old y value. Or if y is in function notation, I can find it using function notation, where I can do f of x2 minus f of x1, where x2 and x1 represent your original x value and your new x value after you tweak it. Because the idea is I'm tweaking that x value and changing it slightly. But sometimes, depending on your function, the computation involved in this is really intense. It might take a lot of computation power in order to actually calculate this. Is there a way I can estimate this value that requires less computation? And the answer to that is yes, you can, using the derivative. Remember that if I write delta y over delta x, change in y over change in x, this actually means something. This is your average rate of change. And we know that average rate of change is very closely related to the derivative, because the derivative is an instantaneous rate of change. So, as long as we assume that delta x is relatively small, and I made a point of emphasizing that by saying we were tweaking x. So if we assume that delta x is relatively small, then this average rate of change is going to be really close to the instantaneous rate of change. Because how did we find the instantaneous rate of change in the first place? We took an average rate of change and let delta x get really close to 0. So if delta x is relatively small, then this average rate of change is close to
the instantaneous rate of change, which of course is the derivative, dy over dx. So therefore, we can use the derivative to estimate delta y by doing the same thing we did earlier, where I can just multiply both sides by delta x. And I get delta y is approximately f prime of x times delta x. We can approximate that change in y using the derivative. So that's where differentials become very, very helpful, is using them to approximate values in a way that requires less computation power, because sometimes finding the derivative and plugging the value into the derivative takes less computation than finding the actual change in y. That takes care of our concept video. Go ahead and try a few of the homework problems out, and then if you get stuck, pull up the examples video where I'll go through a couple of examples, and I'm actually going to focus on the differentials portion of it. Like we said, marginals are just your basic derivatives, so there's nothing too complicated about those marginal problems. So I'll focus on differential examples in my example video, but if you have other questions, please let me know.